me ask a question. Why should the temperature be positive?
It's proportional to energy.
So energy can be positive and negative. So, well, you see, temperature, I didn't say temperature is proportional to energy, by the way. I said that for the ideal gas, the temperature is proportional to the energy. And typically we use the ideal gas temperature, which basically relies on this relation. So if you keep volume constant, N constant, which tells you that pressure is proportional to temperature. So as long as pressure is a positive quantity, temperature is a positive quantity. But again, this is restricted to ideal gas.
Temperature, as it is just, I guess, related to the multiplicity or the other calculations. So if it's zero, then
How is the relationship between the multiplicity?
What I mean by the entropy and the
Okay.
thing is when we get zero, when we get zero, that means entropy
Is zero, fine, but that doesn't tell me why T should be positive. Why not negative? Now you see, we said that everything we will do will be related to this Qn. And Qn is defined as e to power minus beta En. Let me write ER. Summed over all possible microstates. We want this to be some convergent sum. If ER can go to infinity, if we want this sum to be convergent, in that case, beta has to be positive. If beta is negative, e to power minus beta ER goes to infinity as ER goes to infinity. So it just doesn't make any sense. Well, you said that it is related to temperature. Well, you see, the temperature and entropy are related through this relation. Well, if entropy increases with energy, that is what we usually expect. If there's more energy in the system, then there's more ways the energy will be distributed in the system. That means the possible ways, the possible microstates corresponding to that macrostate will increase. Then temperature is 1 over T should be positive. ds over dE should be positive. 1 over T has to be positive. Again, this is under the assumption that the number of allowed microstates increases with increasing energy. But is it always true? Well, let's look at if you consider the kinetic energy, just looking at the kinetic energy, the more energy you have, okay, the particles can distribute this energy in terms of the kinetic energy in many more different ways, so this will still be valid. If there is the kinetic energy, ER can go to infinity, the system can have infinitely large kinetic energy. So again, beta has to be positive. So if we are looking for a system that has a temperature, one is, it shouldn't have any kinetic energy. We should be looking at a system which doesn't have a kinetic energy. So that ER might not go to infinity. Okay, then you can ask, well, all the particles have kinetic energy. But you see, we have been always discussing, we have a system, the environment, or you have a large system, and then we have a subsystem of this large system, and they exchange energy. And at least for me, when I was learning statistics, subsystem was mainly a physical separation. So I have this large physically system, and this small part separated by location. Okay, for me, learning first step was, okay, this separation need not be a physical separation. If you have a mixture, well, each ingredient in the mixture can be your subsystem. So subsystems need not be physically separated. They can be just chemically different, or just pick up some particles based on some criteria, like their chemical property. They can be your subsystem. Or even just pick up certain degrees of freedom. They can still be your subsystem. So the definition of the subsystem in this sense is quite general. So as our subsystem, we can treat some degrees of freedom which don't contain the kinetic energy. Of course, we don't want, you see. So we are looking for a subsystem which might have a negative temperature. But if we are separating the degrees of freedom which don't contain kinetic energy, and then there will be degrees of freedom which contain the kinetic energy, well, those degrees of freedom which have the kinetic energy will have positive temperature. The other subsystem will be negative temperature, so you start with a system which is not in equilibrium. But I also want these two systems to be separated somehow so that they will not reach equilibrium fast. So for a sufficiently short amount of time, I should be able to treat this subsystem as in equilibrium in itself, ignoring the interaction with the environment. Well, all this discussion is, okay, we have kinetic energy. I want a subsystem which doesn't interact with the kinetic energy, that also excludes any degrees of freedom which is related with position. If we have a kinetic energy, position will be changing fast. So that's why I don't want any degrees of freedom related with position. Well, still there are other degrees of freedom besides the position and the momentum, like the spin. Let's look at the spin degrees of freedom. And in particular, let's look at nuclear spins. Because you see, nuclear spins do not interact strongly with neither the linear momentum nor the position. Nuclear spins will be more or less isolated with other degrees of freedom. Again, for simplicity, let's just look at a system of spin 1/2 particles. I'm saying that let's ignore any kinetic energy and the potential energy, basically fixed in their position. Which can be the spins in a solid, the nuclear spins in a solid. Well, their position allows me to separate these, so they are distinguishable systems. And I will assume that this system is in an external magnetic field. So I have this system of spins in an external magnetic field. I can write the Hamiltonian. For each one, this will be minus mu dot B, where mu, let me write it in this form, h power over 2mc, g is the so-called gyromagnetic ratio, in multiplied by the spin. Sorry. Yeah. Let me write it in this form. And since we are looking for spin 1/2 particles, g is equal to 2. So this is, let me write it in this form, minus mu z times b. I will be taking b to be uniform in the z direction. So this will be minus, let me write mu 0 times sigma 3 sigma z times b. Sigma z, this Pauli matrix. Let's write the partition function, Q1. This will be e to power minus beta hi. Well, the microstates are simple. Sigma z is equal to plus or minus 1. So this will be e to power minus beta mu 0 b plus e to power beta mu 0 b. Or let's say twice cosine hyperbolic x. I will call x is equal to mu 0 beta times b. This is our Q1, the partition function for one particle. For n, Qn is just Q1 to the power n. This is 2 to the power n cosine hyperbolic to the power n of x. The free energy minus kT logarithm of Qn. So this is minus n kT logarithm of twice cosine hyperbolic x. This is the free energy. Now what do I need to determine the temperature? Well, temperature as a function of energy, let's say. Let's calculate, we need the energy. What is U? U is, well, let's go step by step, F plus Ts. Entropy is the derivative of the free energy with respect to temperature, which is minus nk logarithm of twice cosine hyperbolic x. But remember, x depends on the temperature. So minus nkt times the derivative of the logarithm with respect to temperature, which is derivative with respect to temperature of twice of cosine hyperbolic x divided by the cosine hyperbolic x. Well, let's write this as the first term is the free energy over the temperature minus nkt. Well, derivative of cosine hyperbolic is sine hyperbolic, so this is tangent hyperbolic x. Times derivative of x with respect to t. I'm just using the chain rule. Derivative of cosine hyperbolic with respect to t is derivative of that cosine hyperbolic with respect to x multiplied by the derivative of x with respect to t. So entropy is minus this one, minus the derivative of the free energy with respect to temperature. So this is plus, this is plus, this is plus, this is minus. So already if I move this first term f plus ts over t is equal to nkt tangent hyperbolic. Remember, x is mu 0 beta times b, or mu 0 b over kt, times this derivative of this term, this which is minus mu 0 b over kt squared. So the free energy of the average energy of this system well, these temp t's cancel on both sides, k's cancel, n minus n times mu 0 b times tangent hyperbolic mu 0 b over kt. This is the average energy. So how does this energy change with temperature? Well, we can look at various limits. If in the limit as t goes to 0, let's say positive through positive values, then tangent hyperbolic mu 0 b over kt, this just goes to 1. So u is equal to minus n mu 0 times b. Well, this is kind of expected because each one of these magnetic dipoles will have a minimum energy of minus mu 0 b. At t goes to 0, well, we expect them to be all in the ground state with a minimum energy of minus mu 0 times b. I have n of them non-interacting with each other, so this is what we had expected anyway. So I was worried about whether we had made a sign mistake over there, but the sign is correct. If you look at the other limit as t goes to infinity, we see tangent hyperbolic x goes to, as x goes to 0. So what is the value at x goes to 0?
Itself.
Is it x? Well, let's see, e to the power x minus e to the power minus x divided by e to the power x. So this is 1 plus x minus 1 minus x divided by 1 plus...
already exists. Limit already exists, you don't need to expand it.
When I said x is equal to 0, yeah, 0. So it goes as 0. It goes as x. So that's why I want to see how it changes. Not the exact value, but how it changes.
It's simply sinh over cosh.
Yeah.
Sinh is sinh.
Yeah.
It exists.
So u just becomes as t goes to infinity minus n mu 0 b times mu 0 b over kt minus n mu 0 squared b squared divided by kt. Well, this is the Curie law for magnetization. We didn't calculate the magnetization, but the average energy is proportional to the magnetization of the system. So the magnetization basically goes to 0 at t goes to infinity. Well, basically what it tells us is if you have infinitely large temperatures, all the spins are just basically randomly up or down. Some of them will have energy minus mu 0 b if they are down. Some of them will have energy mu 0 b up. So it's just equally probable. Both up and downs are equally probable. So on the average, the energy just goes to 0, average energy, and hence the average magnetization. Now what I would like to do is, before that, what are the possible energy values of this system? You see, here we show that average energy as a function of temperature. At 0 temperature, let me move it up. At 0 temperature, we just seen that the energy is minus mu 0 b times n. And as the temperature increases, it goes to 0, it approaches 0. But let's go back to our system of spins. What are the possible microstates of my spins? Okay, on one hand, we have a minimum energy configuration, which is all the spins are pointing in the same direction as the magnetic field. This is the minimum energy configuration. But the maximum possible energy of my system is when all the spins are pointing in the opposite direction, which has an energy mu 0 b times n. So my system has such a maximum energy. Now the problem was, as I increased temperature from 0 to infinity, I never went there. What if I create a system that has an energy U larger than 0? But you see, let's go back to this expression. Can that expression over there, u is equal to minus n mu 0 b tangent hyperbolic blah blah, can it be positive? You see, for negative temperatures, it is positive. So U larger than 0 basically means that T is less than 0. That's a negative temperature system. Now this is the treatment in the canonical ensemble. Let's go to the microcanonical. The same system. Because there I can calculate the entropy directly. So what I want to know is, let's say that the energy of my system is U. And let me assume that this U is mu0 B times, mu0 B times some number. Let me call it small m. The energy of my system, remember, is mu0 B sigma z over all the spins. This is the total energy of my system. Let's say that Ni, N plus, be the number of spins in the direction of B, and minus to be the number of spins in the opposite direction. Of B. N plus plus N minus is just a total number, and energy is basically mu0 B times, so there's a minus sign over here, N plus minus N minus, which is minus mu0 B times capital N minus twice N minus. And N minus can be changed from 0 to capital N, which should be, okay, so this should be equal to mu0 B times M. Well, what does this tell me? If I know the energy of the system, I know the total number of particles, I know N minus. So how many states do I have for a given N minus? Well, I cannot change the N minus, but I can shuffle my spins. It gives me a different microstate, but it doesn't change N minus. So the question is, in how many ways I can shuffle these things, in which I have N minus spin pointing in the opposite direction, N plus spin pointing in the same direction. Well, I have N of them. I can shuffle N spins in this way, but shuffling the same spins doesn't give me a new microstate, so I have to divide by N plus factorial, N minus factorial. This is, or let me write it in this form, N factorial divided by N minus factorial times N minus factorial. And what is N minus? Well, this relation tells me that 2N minus N is equal to M. So N minus is M plus capital N divided by 2. And this is my N minus. So this is omega E. Yeah, omega E. For a given energy, I have this many microstates. Well, the entropy is K times logarithm of omega E. This is K times logarithm of N factorial minus logarithm of N minus factorial minus logarithm of N minus factorial. Well, now the typical, the standard trick of Stirling's approximation, this is k times n logarithm of n minus n minus n minus n minus logarithm of n minus n minus plus n minus n minus n minus logarithm of n minus plus n minus. Well, these terms without the logarithm, they just cancel each other. And I have at the end, let's say this is k n minus n minus logarithm of n minus n minus n minus logarithm of n minus n minus plus n minus logarithm of n minus n minus logarithm of n minus. Well, I'm just doing some algebra to simplify the expression. Let me write it as n plus logarithm of n over n plus n minus logarithm of n over n minus. This is the entropy of my system. Now the inverse temperature is derivative of entropy with respect to the energy of my system. Or this is 1 over mu 0 b times the derivative of the entropy with respect to m. You see, I already know what n minus is. N plus will be just n minus m over 2, because n minus plus n plus is 1, is n. So let me take this derivative of the entropy with respect to m. One over mu 0 b times k, derivative of n plus with respect to m, logarithm of n over n plus, minus n plus times derivative of n plus with respect to m, divide by n plus. It's the derivative of the first term, plus change plus with minus. Instead of n plus, I have the same term for n minus. Okay, just a couple of more steps. Okay, derivative of, just remember these expressions over here. Now, derivative of n plus with respect to m is minus 1/2. And n plus with respect to m is again minus 1/2, so plus 1/2. So this is the first term, first two terms for n plus. Now I write the same terms for n minus. Derivative of n minus with respect to m is plus 1/2. And minus derivative of n minus with respect to m plus 1/2. So these 1/2s cancel. And we end up having k over mu 0 b. Let me take the 1 over 2 outside. I have the logarithm, so this is minus, logarithm of n plus over n minus. This is the inverse temperature. So what does this tell me? If n plus, that is the number of spins pointing in the direction of the magnetic field, is larger than n minus, number of spins pointing in the opposite direction, then the temperature is positive. But n plus, the number of spins pointing in the direction of the magnetic field, need not be more than the number of spins pointing in the opposite direction. So if n plus is larger than n minus, I have temperature is positive. On the other hand, if n plus is less than n minus, more of the spins are pointing in the opposite direction. So basically the system has a larger energy, by the way. In this case, the temperature is less than 0. And this temperature less than 0 corresponds to microstates that have a larger energy than to systems that have a positive temperature. And we do create these systems experimentally also. There are experimental creations, basically using nuclear spins, because nuclear spins don't interact with the other degrees of freedom very much. So you can basically isolate them. What you do is you just create a system in equilibrium, including the magnetic spins, and then flip the magnetic field. So the spins will not flip themselves until they equilibrate. Okay, their interactions with the other degrees of freedom will be small, but not 0. Eventually they will equilibrate. But until they equilibrate, they will create a system of negative temperature. Yes, your question. You had a question.
No means I understood.
Okay. So let's also look at the case. What happens when you bring a system of negative temperature with a system of in contact with a system of positive temperature? So this is a system. This nuclear spins is a system of negative temperatures, and we had just seen that negative temperatures have more energy. Let's see that if it is a general property. You say, how do we study in thermodynamics? How did we study the flow of heat? What we did was, let's just take two systems. One is at some temperature T1, the other one is at temperature T2. And let's assume that we have a heat transfer of Q from T1 to T2. Thermodynamics tells us that the Q should be such that the entropy of the system increases. If T1 was hotter than T2, we said that, okay, the heat will flow from T1 to T2 to increase the entropy. If T1 was less than T2, then we said that Q should be negative, which means that the heat flows from T2 to T1. Now let's generalize that argument to, let's say, what happens that we will assume T2 is less than 0. What should be the direction of flow of heat if one of the systems is negative, has a negative temperature? Well, let's look at the change in the entropy. It is minus Q over T1 plus Q over T2. Well, let's see. Q over T1 is positive. So minus Q over T1 is, sorry, let me write it in a slightly different way. Minus Q times 1 over T1 minus 1 over T2. You see, 1 over T1 is positive, 1 over T2 is negative. So this parenthesis, independent of the numerical values of T1 and T2, as long as T2 is negative, T1 is positive, this is positive. We know that delta S should be positive, but that minus sign over there tells me that Q should be negative. So if we have a system of negative temperature, which we can even create experimentally, heat always flows from systems of negative temperature to systems of positive temperature. In that sense, negative temperatures are hotter than positive temperatures. So it's not, a negative 5 Kelvin is not less than 0 Kelvin, it is mainly larger than plus infinite Kelvin. Of course, these only happen in systems which don't have kinetic energy, in subsystems where there is no kinetic energy involved.
To a negative temperature, we should have more energy.
Yes?
So heat flows from more energetic system to less energetic system.
Exactly.
This makes sense.
Exactly.
But saying hot is not that making any sense.
Why? Why do you think something is hot when you touch them?
Okay, the definition of hot is more temperature is hotter.
No, it's not the, I mean, you see, you had the concept of hot, we had the concept of hot even before we had the concept of temperature.
Yeah.
So the word hot is not directly related with temperature. In ordinary life, everything we observe in our everyday life, we don't observe the nuclear spins. Hotness corresponds to temperature. Hotter means has a higher temperature. But for negative temperatures, it doesn't work. Still, if somehow somebody creates a system with negative temperatures, and if somehow I can touch them with my hand will burn. In that sense, it is hotter.
Yeah, some materials are in lava, but people can just touch it because it's
Oh, that's different process.
Well, I wouldn't like to try that. If the convection is slow, then you won't be burned. But if you keep it long enough, I wouldn't advise it. Same thing holds for liquid nitrogen, more or less. Because you see, there also, there is a vapor formation. If you touch a hot lava, it's basically your sweat. It creates a layer of gas. If you don't touch it long enough, or if you try to walk on it, it might save you. Well, in the case of liquid nitrogen, it is the nitrogen gas that formed by touching your hand that creates this insulating layer. Okay, so I will not torture you further. Any last questions?
I have a question, but I don't know if they are related or not. So, the thing is, this is actually a classical observation. We just assume an extension for a temperature to be negative, and then we see for some spinorial systems, we can have that in a cluster or in some place in the.
Well, you see, when you talk about spins and put classical observations, I have questions because spins don't exist in classical physics.
That's the thing. If I'm not mistaken, for let's say masses, spin particles, with the magnetic field and quantization, we know that the number of the spins are not conserved as an axial anomaly. And in that sense, maybe temperature, the negative temperatures can get higher and higher because the number of particles in the N minus will increase in the sense that we have really a problem.
So next week we will do classical spins. We will just treat this classically where there is no quantization of the sigma z, etc. So there is a classical analog. Secondly, here we are treating a very simple system in the sense that there is no interaction. So there is no anomaly to talk about. So it's just I have this isolated system. The only thing they interact with is the external magnetic field. I have a very simple system. Do I have realistic such systems? Yes, I do. Like the nuclear spins. And I can study them, I can do experiments with them, and I can observe these negative temperatures in such systems. This anomaly and all the rest are really different things.
Can you go back to the energy versus T graph? So should it be the symmetric of this one or the negative temperature?
Sure. You see. Well, this is our expression. Which is, by the way, valid for negative temperatures and also for positive temperatures. So let me draw that as a function of temperature. It's basically the plot of tangent hyperbole. Let me say that this is t equal to 0. Let me call this point t is equal to plus infinity. And this point as t is equal to minus infinity. And this point over here, t is equal to 0 minus, this is 0 plus. So the plot is more or less something like this. It starts from minus n mu 0 b, it will go up to n plus n mu 0 b, it will cross this line. So it will be something like this. You see that t is equal to plus infinity and minus infinity, u is 0. So in that sense, there is no discontinuity at t is equal to infinity. If you would draw the entropy as a function of energy, you see the minimum energy is minus n mu 0 b. The maximum energy this system can have is n mu 0 b. At minimum energy, we have a single state. All the spins are pointing in the direction of the magnetic field. So the entropy is 0 at u is equal to 0. At maximum entropy, maximum energy, all the spins are pointing in the opposite direction as the magnetic field. So again, B is equal to 0. S is equal to 0. So what happens is, as you increase the energy from minus n mu 0 b, the entropy increases, but eventually it flattens out, and then it decreases. And remember, 1 over t is derivative of entropy with respect to energy. You see, up to here, this is u is equal to 0. That the entropy is increasing as a function of energy. So that derivative is positive, and hence temperature is positive. Above u is equal to 0, entropy is decreasing as the energy is increasing. And hence that derivative is negative, so the temperature is negative. But of course, this entropy going to 0 at higher and higher energies appears only if there is an upper limit on the energy. For example, for kinetic energy, as you increase the energy, there are more ways you can distribute the energy among the kinetic energies of the particle, even if you don't consider the potential energy. But for spins, if you increase the energy higher and higher, eventually you end up having a single state with the maximum energy. So entropy goes back to 0. Any other questions?